Hey, sorry for the abrupt ending on the video there. I need to keep under YouTube's 15 minutes, which I learned with the last one. But here's the PHET skate park sim that I was talking to you about. Um, this is the intro page. We'll go ahead and turn on all the toggles here. This is a really great way of visualizing the whole interplay between kinetic and potential energy, and even seeing how friction comes in. Now, in this page, we don't have friction yet, so I'll go ahead and put our skater right up here at about the 6 foot mark or 6 meters, and let the skater go. And we see that the skater does not lose any height. Now, like I said, there's something we're missing here, and yeah, it's friction. So in a frictionless environment, if you were to go on in a skate park like this, you would actually be able to maintain the same height, up and down, up and down. And watch the pie graph there, and also the bar graph, and you can see how, and I'll kind of put this in a slow motion so you can see a little bit better. As the skater goes down, kinetic maximizes, potential minimizes, but the top of the ramp, you see potential is maximized, like right here. We have maximum potential, zero kinetic. We have zero kinetic because momentarily the skater's not moving. It's just like throwing a ball up in the air. I've told you that at the very top of the arc, the ball is stationary. Same thing here. And then as the skater goes back down, once they reach the very bottom here, about like that, we see that now kinetic is maximized because there's zero potential energy, because there's zero height above the ground. So that's going to come in really handy when you're solving problems, is knowing that interplay. And then if I kind of go right here, I'm at roughly half and half, which means that about half of my total energy is kinetic and about half is potential. So if I knew the height here, which I'm a little above 3 meters here, I could plug that into my PE equals mgh. And if I knew the person's mass, I could solve for the potential energy. And then if I knew the total energy, then I could find the kinetic energy, and I could use the kinetic energy to find the speed, just like you saw in the Bozeman video. Now, if I introduce friction into this whole scenario, it's going to look a little bit different. Notice we started a little below 6, but look what happens. We start to lose height as we go, because what's happening is that energy is being dissipated into thermal or friction energy. Think about, I was rubbing my hands together in case you couldn't tell. When you rub your hands together, what do you feel? You feel heat. That's friction between your hands, so that heat is being dissipated, so that energy. You might look at this and be tempted to think, well, wait a minute, you said conservation of energy, it doesn't go away. Well, it didn't. It all that kinetic potential energy transferred into thermal energy. I'll let you see that again there. And then I forgot to do this on the other one, but I'll go ahead and do it here. If I have this on, I can set the skater going, and the skater goes off screen. But watch what happens. We're assuming the skater is continuing on a flat run, so their kinetic is slowly turning into thermal, but potential still zero because there's no height there. You can also click on this one right here. Now watch what happens. As they go up, they're going to continually lose height until they can no longer overcome that. By the way, this is pretty much the basis for how roller coasters are designed. Whatever you're starting at, you never want a hill that's higher than where you start at, because law of conservation of energy says you're not going to make it unless you have some sort of external power, which usually coasters are just gravity based. So I start here, but then and also of course with a roller coaster you're going to want to know exactly, you're going to want to have some friction obviously, but you want to kind of minimize it so you can get that coaster going faster. Of course, there's other things involved, but that's kind of the gist of it. And then finally, we have the playground, which you guys can get into however you like. You can set these up like this. Have my skater kind of go like that, and of course they're gonna, well, fall off. Or, oh yeah, you can also have them attached to there. So there's all kinds of things you could do with this. We're actually going to do a problem a little bit later on where we're going to examine the whole concept of the loop-to-loop and how that goes with it. Now, I didn't get a chance to say in the first video, but I also want to look at classwork problem number 5, which, if you read ahead, involves the super balls. So if you have a bouncy ball and a meter stick at home. You need that to be able to complete this. I'm going to film myself doing it, so if you don't have those things at home, just kind of follow along with what I do, and I'll talk you through kind of the basics of that as well. So I'm going to try to attach that to the end of this video, so hopefully you're going to see a little bit of a pause, and then you're going to see me.